Hi everyone, in today's video we will go through the details of the TI F28379D Launchpad, which is a powerful dual-core C2000 microcontroller specifically designed for real-time control applications like motor control, power electronics, and digital power conversion. Before we dive in, I want to mention that we won't go into every single detail. There is plenty of in-depth documentation available online from TI. Instead, we will focus on the key modules that matter most for motor control engineers and real-time applications. The F28379D features dual 32-bit C28X CPUs running at 200 MHz, making it ideal for demanding controller algorithms. This is a diagram I downloaded from the Texas Instruments website. It shows the different components on the board, and you can use it as a reference while I walk through each of the key modules. Let's talk about the specs that really matter for motor control engineers. The board has 1 MB flash memory, which is more than enough to store complex motor control algorithms, including advanced techniques like field-oriented control, sensorless operations, and multi-motor coordination. It has 204 KB of RAM. This provides ample space for real-time data processing, buffer storage, and fast execution of control loops without performing bottlenecks. The board includes a dual-core microcontroller. One core handles high-speed control tasks while the other manages communication, diagnostic, or user interfaces, enabling true parallel processing. With a 200 MHz core clock, the microcontroller can execute control loops extremely quickly, essential for real-time feedback and stable operations in motor control applications. Together, this memory and processing configuration makes the F28379D well suited for demanding applications such as field-oriented control systems, motor control, and even multi-motor system where timing and precision are essential. GPIO, General Purpose Input-Output, is fundamental to any control system. It's the interface between your microcontroller and the real-world sensors, drivers, switches, LEDs, and more. The F28379D provides 169 GPIO pins, offering exceptional flexibility and scalability for complex control applications. Let's look at some of its key features. First, each pin is individually configurable. You can set it as an input, output, or route it to a peripheral function like PWM or LDC. This gives you maximum design freedom without needing extra external components. Second, these GPIOs have fast switching capability, which is essential for critical signals like enables disable lines for gate drivers or real-time status feedback. Speed matters when you are protecting your power stage from faults. Third, built-in pull-up and pull-down resistors eliminate the need for external resistors, saving board space and simplifying circuit design. And one of the most valuable features, input qualification. This allows you to filter out noise or digital inputs using hardware-based digital filters. In motor drive environments where electromagnetic interference is common, this is crucial. For example, if you are reading a fault signal from a current sensor or monitoring an emergency stop button, you don't want false triggers due to voltage spikes. With input qualification, you can configure the GPIO to ignore short duration noise pulses, ensuring reliable operation even in noisy industrial settings. So what are some practical uses? The first one is enable disable signals for gate drivers, which is turning power stages on and off safely. Fault detection inputs from current system. Sensors feeding real-time protection logic. Status LEDs and user interface elements giving visual feedback during operation. Emergency stop inputs with hardware qualification, which is used in making them robust against electrical noise, and communication with external devices such as encoders or other controllers. In summary, the GPIO subsystem on the F28379D isn't just a basic input-output block. It's a powerful, flexible, and noise-resilient interface that directly supports reliable and safe motor control systems. The Enhanced PWM module, or ePWM, is the heart of any motor control system. It's what drives the power electronics in your inverter, generating the precise switching signals that control motor speed, torque, and efficiency. The F28379D features 12 ePWM modules, and each one can generate up to 2 independent PWM outputs. This gives you a total of 24 PWM channels, more than enough for motor system or complex drive topologies. Let's break down what makes these PWMs so powerful. First, they offer 16-bit resolution with flexible frequency controls. This means they can achieve extremely fine control over your duty cycle, which is critical for smooth motor operation and minimizing torque ripple. Second, hardware dead time insertion is built right in. This is essential for protecting your power stage. In a typical inverter, if both the high side and low side MOSFETs turn on at the same time, you get a short circuit called shoot through. The ePWM module automatically inserts a small delay between turning off one switch and turning on the other, preventing this dangerous condition, all in hardware with zero software overhead. Third, it includes advanced protection features like trip zones. If a fault is detected, say an overcurrent or overvoltage event, the trip zone can instantly disable the PWM outputs, shutting down the inverter within nanoseconds. This fast response is crucial for reliable and safe operation. Now let's look at some features specifically tailored for motor control. The first one is complementary PWM pairs. Each ePWM module can generate a pair of complementary signals, perfect for driving half bridges in three-phase inverters. One signal controls the high side device, the other the low side, with automatic dead time handling. The second is synchronization between PWM modules. All ePWMs can be synchronized using a common time base. This ensures precise timing across all the phases, vital for balanced three-phase operation. The third one is event trigger capability. You can use PWM events to trigger ADC conversion at exactly the right moment in the switching cycle. For example, sample the current just after the switch turns on, when the reading is most accurate. This enables precise current sensing without relying on software timing, which can introduce jitter. And finally, chopper control mode. This allows for fast current regulation by rapidly adjusting the duty cycle based on the feedback. Useful in applications like sensorless control or active damping. So how does this work in practice? For a standard three-phase motor drive, you would specifically use three ePWM modules, giving you 6 PWM outputs, one for each leg of the inverter. The hardware dead time prevents shoot-through, while trip zone provide instant protection during faults. And by triggering ADC sampling at specific points in the PWM cycle, you ensure your current measures are taken at the optimal moment, maximizing control accuracy. So in short, the ePWM module isn't just a timer, it's a full-featured real-time control engine designed specifically for the demands of motor drives. Accurate analog measurements are the foundation of effective motor control. Without reliable feedback, you can't control torque, speed, or position with precision. That's where the analog to digital converter or ADC comes in. The F28379D features 4 independent 12-bit ADC modules labeled ADC A, B, C, and D. Gives you up to 24 analog input channels in total. This means you can monitor multiple signals simultaneously, currents, voltages, temperatures, and more, all on one chip. Let's look at what makes this ADC system so powerful. First, it supports a sampling rate of up to 3.5 million samples per second. That's fast enough to keep up with the high-frequency control loops, essential for modern motor drives that operate at tens of kilohertz. Second, it has simultaneous sampling capability across multiple ADCs. This is critical when you need to measure two or more signals at exactly the same point. Like phase current in a three-phase motor, if the samples aren't synchronized, your control algorithm could see errors leading to torque ripple or instability. Now let's talk about how these ADCs are triggered because timing is everything in real-time control. Each ADC module has 16 startup conversion channels. These are like programmable triggers that tell the ADC when to sample, and here is the key. Each startup conversion can be triggered by different events, not just software but hardware events that happen precisely when needed. For example, PWM events, which is the most common trigger for motor control. You can set an ADC to sample right after a PWM cycle starts or at its midpoint. Time events useful for periodic sample outside of PWM timing. Software triggers for manual or diagnostic sampling, and even external signals if you are interfacing with sensors or other systems. This flexibility gives you full control over your sampling strategy. So what does this mean in practice? Let's say you are controlling a three-phase motor. You want to measure two-phase currents at the exact same point, ideally at the center of the PWM cycle, where the current is most stable and accurate. You can configure ADC as state of conversion 0 and start of conversion 0 and start of conversion 1 to sample two-phase currents simultaneously, triggered by ePWM1 reaching its center point. This ensures perfectly synchronized measurements, no jitter, no delay, and no software overhead. And since the ADCs are independent, you can also use another ADC module to monitor the DC bus voltage or temperature sensor at the same time, all coordinated through hardware. In summary, the ADC subsystem on the F28379D isn't just fast, it's intelligent. With its high resolution, high speed, simultaneous sampling, and flexible triggering while startup conversion, it delivers the precise, timely feedback needed for robust and responsive motor control. Precision timing and fast interrupt handling are what make real-time motor control possible. The F28379D gives you three 32-bit timers for general tasks, like scheduling communication or slow loops, plus a watchdog timer to recover from crashes. And cleverly, the ePWM module themselves can also act as timers, doubling their utility. But the real power comes from the interrupt systems. With up to 96 peripheral interrupts managed by the PI module, every sensor ADC conversion or fault tolerance signal gets its own dedicated trigger, and they are prioritized. So if an overcurrent happens, the fault interrupt jumps ahead of everything else, shutting down PWM outputs in microseconds before damage occurs. Now here is how it works in practice. Your current loop runs every PWM cycle, say at 20 kHz triggered by the PWM module itself. Your speed loop runs slower, maybe 1 kHz using data from the fast loop. Communication tasks like CAN or UART happen on a time-based schedule, and fault monitoring always highest priority. All this happens simultaneously, no software delays, no jitter, thanks to hardware, triggered events, and fast interrupt response. In short, precise timing plus intelligent interrupts equals reliable, safer, and high-performance motor control. Communication is vital in modern motor control systems. The F28379D includes SPI for fast peripheral communication, I2C for sensor interfacing, UART for debugging and external modules, CAN for robust industrial networking. Precise position feedback is critical for advanced motor control. The F28379D integrates eQEP modules for incremental encoders, resolver support for absolute position measurement, and built-in velocity calculations hardware. These features enable tight position and speed control loops without requiring heavy CPU overhead. Debugging is an essential part of any development workflow, especially in real-time control system where timing and precision matters. The F28379 Launchpad comes with an onboard XDS100 V2 debugger, which gives you powerful debugging capabilities right out of the box. You can perform real-time debugging without stopping the system, meaning you can monitor variables, trace code execution, and inspect register while the motor is running. That's critical for catching timing issues or transient faults. Plus, it supports dual core debugging, so you can debug both CPU cores simultaneously, one handling control, the other communication or diagnostics. And because it integrates tightly with the Code Composer Studio, setup is fast and debugging feels seamless. This means faster troubleshooting, smoother development, and the ability to validate performance directly on hardware, all without extra tools. So the F28379D is a powerful yet cost-effective dual-core C2000 microcontroller, packed with rich peripherals like advanced PWMs, high-speed ADCs, and flexible GPIOs, all designed for real-time motor control. Its dual-core architecture enables true multitasking. One core runs your control loop at higher speeds while the other handles communication, diagnostic, or user interface tasks, making it ideal for complex applications like multi-motor systems or sensorless control. And to make development faster and easier, TI provides the motor control software development kit. a complete software framework with drivers, examples, and tools that help you get up and running quickly. So whether you are building a prototype or scaling to production, the F28379D delivers performance, flexibility, and support, all in one compact, efficient package.